this PWM that we've been talking about, let's before we talk even more about it, like how you set it up and all this kind of stuff, let's give an example of how we'll use PWM. PWM, for the most part, is used for driving motors. And again, when you're driving just brush style motors like we're going to, you only need one PWM channel to drive a motor. When you start talking about what's called brushless DC motors, you have 3 phases. And those phases are generated by 3 PWM signals, or who knows, maybe more. Again, I wish I had more time to play with brushless DC motors. Chinmay is going to be helping me out, right, Chinmay? We're going to get going on 3-phase motors a little better. But anyway, for us, it's a little bit simple. And so that's all these extra registers and all these extra functionalities are for more advanced motors than what we're dealing with. But let's give you an example. Why do we need this PWM? So with our little, what's called an H-bridge, and we'll talk about the innards of an H-bridge later in the semester. But for now, all you need to know, there's a chip on the robot. Actually, it's not on the green board of the robot or the red board or anything like that. It's actually towards the front of the robot, and there's a little H-bridge chip that's actually set up perfectly for the motors that we have on this robot car. The motors can take up to a maximum of 2 amps, and this little chip can drive up to 2 amps also. So I kind of spec'd it out for the exact motor. But what we have is our DC motor, and a lot of times you draw a DC motor with its commutators like this, and then the rotor is the circle in the middle, right? This rotor turns, and that's what's turning our wheels. Obviously, this rotor is turning gears, and then those gears through shafts are connected to our motor, to our wheels. And actually, you'll know we have 4 wheels on those robot cars. The 2 sides are belt driven, so there's only 1 motor per 2 motors, 1 motor per side. So it's a skid steers type of robot for our case. But anyway, so we have 2 H-bridges, right? Because 1 for each motor. And this takes 24 volts as its power source, okay? Then, in addition, there is an enable wire. I can't remember if it's active low or active high, doesn't really matter. And then we've got a switch. There's again a pull-up resistor, 3.3 volts, a switch to ground. Something like this. That's a little more complicated than that, but that's a good enough way to drive. I have a way that when you flip on the power to there's a little safety circuit in there. When you flip on power to the robot, it can't be enabled until you actually flip the switch. So there's a little flip-flop in this circuit. I don't want to draw that up there. But in a sense, what you have to do is flip the switch to enable the H-bridge. Okay, you'll see, you get, until you get used to it, you'll be like, Dad, my robot's not moving. And I'm like, did you flip the switch? Oh, yeah, so you forget. So we'll do that for a couple weeks till we get that in our head. But anyway, so we have a way to enable this. If it's not enabled, the motor won't move. And then finally, we have the direction pin, which is kind of interesting. You could, if we can get into this more, you could actually PWM the enable pin, and then just direction is a high or low, depending if you want to go positive or negative. Positive direction or negative direction. Well, with this little H-bridge, after studying the data sheet of it and all this, I found that they recommend for more linearity. So in other words, you give a command and it produces a certain amount of current, give another PWM command, it's a proportional higher current, for example, more linear. You pulse width modulate the direction line, which is kind of interesting when you first think about it. So this direction line, what does it do? So let's see, direction, when it is high, when the signal coming to it is high, so when the signal is high, the voltage coming into the direction pin, I mean by that, right? So when it's sitting at 3.3 volts and the H-bridge is enabled, that's telling the H-bridge to drive maximum current to the motor. in the positive direction. Okay? So if you had a switch here, which we don't, but let's say you had a switch right here, you flipped it to high voltage, the motor would give max current, your robot would boom, take off, right? As fast as it can in the positive direction. Then somehow you caught the robot, and then you flip the switch to low. When the direction line is low, that's telling it to drive full current in the negative direction. So you put the robot on the floor, flip it low, and boom, it would take off in the negative direction. Right? So at first thought, that doesn't seem like a very good control, does it? Even so, let's say, okay, great. Dan says we pulse width modulate this. All right, what does that mean? Let's try it. We're getting an example here. But let's say you give the direction line this signal where it's high for 1 second and low for 1 second. So this would be called a 50% duty cycle, wouldn't it? 50% on, 50% off. But the key is here, we're leaving, not millisecond, our example right now, we're doing 1 second on, 1 second off. Boy, now just think about that. For 1 second, the motors are getting max current. So for 1 second, this robot's going this direction, Then after a second, it's switched to low, and so the robot's told to go back the other way really fast. So your robot's going to go, we don't like that, right? It's still not very good control, is it? Okay? But what if we speed that up again, right? This is trying to get you the idea of what this pulse width modulation is doing. So what if we now turn it on for 0.1 seconds? The time constant of this motor, it gets up to its full speed in about 0.3 seconds, about 300 milliseconds is the time constant of this. So what do you think your robot would do if you were given this kind of signal? Yeah?
Stand still.
Not quite yet, but yeah, we'll get into that. That's right. 0.1, it would kind of chatter, wouldn't it? 0.1 seconds is pretty long. So your robot would sit there, kind of do like this, okay? But you're right. Now if I keep on speeding that up, and go to whatever, like 0.0, so a millisecond, you're right. Then the robot's just going to sit there. Now the problem with this, though, is when you turn on a handheld drill, you hear the gearing going usually, right? You hear that gearing, but also a lot of times, what happens when you jam the torque? The drill. You hear kind of a little bit of a whine. You heard that before. That's probably a lot of reasons. One is the current's stalled out and all that kind of stuff, but also that could be due to the frequency that you're pulse width modulating the motors of that drill. Okay? Here, what would we hear? We can hear 1,000 hertz, can't we? Actually, 1 millisecond on, 1 millisecond off is 500 hertz, isn't it? 2 millisecond period. Agree with that? 500 hertz signal. We can hear that, and actually you would hear that. The motor kind of turns into. Have you ever turned on a little quad rotor? Bought one of those little cheap quad rotors or whatever. Sometimes when they turn on, they kind of go beep, 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 right? Those are not being played by a speaker. Those are being played by the little DC motors on that quad rotor. The coils in there and how they actuate that rotor actually makes a noise. Okay? So if we pulse width modulated at this frequency, even though the robot would probably stay pretty still, it may chatter just a little bit at that 2 millisecond, that would still be 0, but we would have a really annoying noise in our ears. Okay? We would hear that. So for our sanity is one reason, but also just to even filter it better, we go with the even faster frequency. Okay? And so what we're going to use, and it also is dependent on this H-bridge. You got to look at the specifications of the H-bridge and see how fast you can turn on and off these signals going into the H-bridge. A lot of industry, from what I understand, the more expensive controllers that are in industry, they usually run at about 80 kilohertz is what I kind of have heard. Haven't played a lot at that range. Most of mine, I stay around 20 kilohertz to 40 kilohertz when I'm playing with my PWMs. That's about the range of these cheaper, inexpensive amplifiers. And so that's what we're going to do. We're going to pulse width modulate this motor at 20 kilohertz, which is 0.05 milliseconds, right? 50 microseconds. So that means we are 0.025 milliseconds. Now let's do this right. We'll say 25 microseconds on when we want to output 0 and 25 microseconds off. And when you do that, we're at 20 kilohertz. Our ears can't hear that. Thank goodness. Maybe a dog come into our lab and really have a headache or whatever, right? I don't know what can dogs hear, or whatever. So that's one of the reasons we go quite a bit faster. We could go faster, but you'll see if you keep on going faster and faster, you start losing resolution of your PWM. And you know, if we could go faster. We could go 100 kilohertz, but we did with this 100 kilohertz. What? That would divide by 4. Right now we only have 2,500 divided by 4. Yeah, you'd be down to only like 500 different PWM duty cycles you could output. At 20 kilohertz, we only have 2,500 different outputs, and I'll explain that too. All right, very good. So this then, we know this is our 0 command. The robot does not move. The motor does not move if we give it a 50% duty cycle. But now, what if we don't do 50% duty cycle? What if we now are off more than we're on? And again, I'm trying my best to do it right. This is staying, I'm trying to be consistent there. So always say 35% duty cycle or whatever this is, right? Which direction would the motor spin?
Would you go backwards?
It would go negative, wouldn't it? Little, not super intuitive, but you think about it, the response of the motor, it does, this makes it go forward, and then this makes it go backward, right? And I'm exaggerating here, but it generalizes finally after, just a couple periods, it finally just looks like the motor, if I'm going, this is time and this is 0 velocity of the speed of the motor, then what happens is this thing's going to, at its time constant, it's going to drop down and start spinning in the negative direction as a proportion to the duty cycle. So, or better, spinning is one speed, but better is that if you just think about holding that motor without it spinning, the drive, the PWM duty cycle is proportional to the torque, the current that's driving through the motor. So when you give it 50% duty cycle, there's no current going through the motor. Okay? Generally. Yeah, there's harmonics and all this crazy. That's why we hear it in our ears. So there is some current, but we're going to filter that all out in a sense. It's generally passing 0 current. Then if we start giving it larger duty cycle, right? 51%, 52%, 53% duty cycle, we start driving current in the positive direction, don't we? Proportional to the duty cycle. Go less than 50% duty cycle, we start giving negative current, so the motor spins in the negative direction. What do you think about that? Make sense? So if we give 75% duty cycle, that's 50% of the way up to 100%, isn't it? So if we give 75% duty cycle, we should be driving the motor with 2 amps. With 1 amp, 2 amps is our max. So if 2 amps are our max, we're giving 75% duty cycle, that would be driving 1 amp into the motor. You see that? 50% is 0, 100% is full positive. So halfway between that, 75% is 50% of the current. Does that make sense? Going the other way, 25% would be 50% of the current in the negative direction. So that'd be negative 1 amp being driven to the motor. 0% duty cycle would be negative 2 amps driven to the motor. So it's all proportional there. Good? Okay, excellent. So this is why we need to figure out how to create the correct carrier frequency, right? The rate at which this repeats. And then have a way to change the duty cycle. Okay? Kind of agree with that? You'll be playing with this. If we have time when you get checked off this, we will definitely be doing it in lab this week. But if we have time while you're checking off, I'm going to try to get you to scope this so you can see your PWM that in homework this week is just driving an LED. Okay? And I just picked it. We are going to drive the LED for homework at a carrier frequency of 5 kilohertz instead of 20 kilohertz. Okay? Good. Anyway, so we've got to figure that out. Now, and we're going to do some examples here in just a second. First, one other thing is, okay, great. So Dan, you talk about this square wave, this duty cycle changing square wave. Where is it inside our CPU? How do we get it out to the world? Okay? Well, that's where we get into this thing called the PinMux table. And you have these things too. I don't know how much you guys have done with Raspberry Pis, but if you get have you ever gone and taken a Raspberry Pi and looked at its little flyer that comes with it, or you find it on, if you type pin out of Raspberry Pi, you'll see, actually let's do it. Let's do it. So what I'm trying to get at is many processors do this. Pin out Raspberry Pi 4. Bunch of pictures here. Let's see if we can find a good one. Yeah, now this is kind of good. Here. So there's actually more functionality than this. But notice here how pin 35 is GPIO 19, but it also can be SPI 1 master in, slave out. We're going to talk about that soon. By the way, there's an SPI question at the end of homework 2. We probably will be lecturing on that the Monday before you're due, so you may want to hold off on that one. You probably won't get to lecturing about the SPI until that Monday before it's due on Wednesday. But anyway, just so you know that. This can have these two functionalities. These other pins, 11, can have those two functionalities. Okay? They cannot have the same those two functionalities at the same time. You have to pick. So in either a GPIO, when you see a GPIO pin, you can use those for turning on and off things. Relays, well, you do it LEDs, but you can turn on and off a relay. You could turn on and off a transistor to make something just like a relay. What else? You can output to a chip to turn it on with a chip select signal, things like that. You can also turn it into an input. That's why I/O, input, output. You could read in a switch. You could read in the state of an I/O pin that's coming from another device. All sorts of different things you could do with those. But if you decide you want to use the serial peripheral interface, you no longer have GPIO 19 to do that with. You would have to pick a different GPIO. Does that kind of make sense? So before, when you're deciding what, now right now we're not doing Raspberry Pi. I just pulled this up to show you a nice chart. Our breadboard, the F28379D, also has what all its pins can do. Yes, it could be a GPIO, but it can also be this functionality. And that is listed in a table that I give you a link to. It's right here. So if you go to the laboratory under homework 2, right here, the PinMux table for homework breakout, the green board, where are all our signals? So let's see here. Let's go to it right here, PinMux table. Now a little more, the Raspberry Pi's chip also has a lot more pins that come out to the 40-pin header. So there's in the data sheet for the Raspberry Pi's processor, there would be a big long chart like this too, because there's a gazillion pins on that processor. All right, anyway, so these are all our pins of the 28379D, and what I'm going to ask you in homework is, it ends up that LED 1, I did it for a reason, I wired it to GPIO 22. Okay? So far, when you've been playing with the LEDs, you've been using GPIO 22 to just turn on and off an LED whenever you wanted to in your program. Now what I'm asking you for homework 2 is, instead of making it GPIO 22, I want you to change it to ePWM 12A. Okay? When you do that, and I'll show you how to do that in code, when you do that, it is no longer GPIO 22. You can talk to GPIO 22, but it's been muxed to not get out to the world. So you got this switch or mux or whatever, multiplexer inside the CPU for that pin, and if you set the mux to ePWM 12A, then this little unit that's ePWM 12, its output pin goes out to the world, out to that pin. GPIO 22 is sitting inside the processor. Yeah, you could turn it on and off. There'd be no reason, because it doesn't get out to the world when you've multiplexed it this way. Okay? And so this is stuff we kind of skimmed over. I should have started CodeComposer earlier. Let's see if I can pull it up quick. So there's a setting, and we have to set this up in main. And so as we get more and more complex code into other peripherals and all that, that's a decision we're going to have to make. And actually, I kind of just tell you in the lab, I say, set up this GPIO pin as SPI pin or something like that, right? And okay, there we go, launch. And that's what you got to do. Otherwise, and so it's always, you look at the data sheet and it says it's got 160 GPIO pins. And then it says you've got 4 serial ports, you've got 3 SPI ports, and all, they list off all of these things you have. But the trick and you got to always remember, and you always get frustrated in that you can't get all those things out to the world at the same time. There's a limit to the number of pins this processor has, and so a lot of things get unused. Okay, is what ends up happening, which is fine. But that's how it works. You don't have all these. You can't get all those peripherals out to the world. Okay, here we go. Well, and that makes sense too, because you normally don't use all the peripherals. But let's go look at, just to show you, this PinMux is set up right here. Where's my lab main? Here we go. So here in initializations, this right here, set up PinMux. So we're setting up GPIO. This is always the GPIO pin, because every pin does have a GPIO labeling. So GPIO 34, we're setting up as MUX 0. So let's go look what that means. So if we go to the MUX table, GPIO 34, oops, where am I at? Where's my mouse? There we go. GPIO 34, come down here, here it is. And 34, if we go up now into the table, 34, actually you could set it to 04812. Again, why they did that, I don't know. But if we put 0 there, so it's GPIO 34. Does that make sense? Now, if I want to make it these other ones, I set it, see the top line? I can either set it to 1, 2, 3, 5, 6, 7, 15. All the other ones are reserved. You'll see that with processors, well, besides those other ones, they do a lot of reserve settings, so that if they need to add things to future processors, they've got room to do that. So you'll see a lot of reserves. Anyway, so for example, 14 is nothing. But, so when we get to 22, right, instead of it being GPIO 22, we want to make it ePWM 12A, so that means we have to set the MUX to 5. Is that clear? So what we would do in our code is we'd come down here, here it is, GPIO 22, all we have to do, set that to 5. Okay? Now, no longer does your program have direct control over that pin. You have indirect control over that pin by setting up PWM 12's peripheral. And however you set that up, then that output pin starts doing what you've told the PWM to do. Okay? Goes out to the world. Now, technically, right here, look at these next commands. You can leave these, but right here you're setting GPIO 22 to an output pin. You can do that, but it's not going out anywhere. Okay? Because it's muxed to be PWM. Now, so you could comment those out, or you could leave them there, whatever. And then this clears that GPIO pin. That again, it's not going anywhere. Doesn't hurt anything, but it's outputting to inside the chip and doing nothing. Okay? Good. Good, good, good. All right. So that's how it gets out to the world. Now, let's do some examples here, because you're going to, and this is throughout the whole semester, we're going to be doing these, figuring out periodic rates. Okay? A lot of times those periodic rates is how fast code is running, how often you get interrupts and all this kind of stuff. But in the case of a PWM, it's how often is our PWM signal repeating. Right? That's also a periodic rate. So we'll hold off on the 20 kilohertz. That's what we'll be doing in the lab, and yeah, in the lab. So let's think about this. Let's say we wanted to create a let's do a 32 kilohertz carrier frequency PWM signal. Okay? And for now, and let's say initially we want it to be 20% duty cycle. All right? Now remember, what do we have to make that happen? That's where this little picture comes in. Okay? And we have the registers TB counter, timer base counter. We have the register timer base period. And we have the register, I don't know why they don't put TB in front of this one, but it's just called CMPA, compare A. Okay? Those are the main registers we have to deal with. Now, we do have a couple other registers for these actions. So what we're, just know, and you'll get this set up, and by the way, when we're working with PWMs in this class, we only do up count mode. We never, anything with down count mode, ignore, leave it at this default. So we're doing up count mode. So that means TB counter is always counting up. What does it do? Does this, hopefully this chart makes sense. See, TB counter's value is on the Y scale. X is time, right? And every clock period, which we got to talk about, I'll draw that up there, TB counter gets incremented by 1. And so it goes 1, 2, 3, 4, 5, 6, 7, very fast. All the way up to the value we've put in TB period, and then repeats everything again. So I guess you could consider that jump from period's value down to 0 is kind of like a down count, but that's just really a rollover. It just resets. It's not really a down count. It's a reset. Back to 0 and it starts again. Okay? All right. And what we're setting it up, let's not, for now, don't worry about ePWM B. We'll do that. We'll get to the B peripheral pin in, which one is, I think, lab, homework 4 or something like that. Don't worry about it. For right now, for this lab and for our programming our robot, we're just using the A channel of our PWM. Okay? And so what happens is when the value in TB counter is 0, we set the output pin, the PWM 12 pin, for example. When the counter value reaches the compare A value, the pin is automatically set low. Okay? The PWM peripheral takes care of that for you. You don't have to do any code to say set it low except for the initializations. And then see, when it happens, it becomes 0 again, back down to 0, it's set high again. Stays high until compare A, goes low, and does that repeatedly now. Okay, so remember our diagram. We want to do this 32 kilohertz. For this, when you draw this, we are going to always remember that we've got 50 megahertz coming in, a square wave, that goes through a divide that we can set. Right now we're just dividing by 1, so that what's coming out of that divide is still 50 megahertz. Oops, megahertz. That is, in a sense, I kind of push it, it's making the TB counter register count up at a rate of 50 megahertz, or in other words, the unit of time, it counts up by 1 every 1 over 50 million seconds. You agree with that? So we know if it counts up to 10, how much time has gone by? 1 over 5 million. That amount of time has gone by in seconds. Agree? If it counts up to 100, we got 1 over 500,000 in time, don't we? See what's going on there? So we can specify how much time to go by. So I like when I'm deciding what things need to be, right? We need to what? We need to set up TB period. We said 32 kilohertz. So TB period needs to be a number. Now, I'm sure we probably can get 32 kilohertz, but obviously there's some frequencies we can't get exactly. We'll get as close as we can to 32 kilohertz. But anyway, we need to set TB period to the value that equals what? The amount of time 1 over 32,000 seconds. Do you agree with that? Okay. So, what can we do? It's pretty simple to find this value, isn't it? We take this amount of time and divide it by this amount of time. Because this is our unit step of time. Do you agree with that? This is the amount of time we want to count up to. And then repeat again. So, I like thinking of it this way. If you like thinking of it in frequencies, go ahead. But I just think that in units of seconds makes more sense to me. So you take and divide by 1 over 50 million. So, of course, it's 50 million divided by 32,000, isn't it? Is the final answer. So, let's do that in the calculator. 50,000. Oh, I'm in programmer mode. Let's get out of there. Scientific. 50, 1, 2, 3, 1, 2, 3, divided by 32, 1, 2, 3. Okay, so we can't get 32 kilohertz exactly. We're pretty darn close. Okay? So you could go a little above 30, let's see, a little below 32 kilohertz by making it 1563. You could go a little bit below, a little bit faster if you made it 1562. But boy, that's really close. Okay? See what I'm doing? So TB period would be set to 15. Let's just do 1562. What do you think about that? Now, what would we set the compare A to get 20% duty cycle? Somebody. You don't even need to know the number. What do? We take 1562 and multiply it by the duty cycle. 0.2, right? What do you think about that? Now, of course, this is the compare A is only a 16-bit value, and it's an integer. So if that has any rounding to it, I guess it won't. Well, it would. It would. It'd have some rounding to it. We would just get it to the closest thing to 20% duty cycle. Right? This times 20 would be what? It would be 3, what is it? 34 or something like 340, something like that. No, what is it? 312. Okay. Yeah, that sounds right. 312, yeah, exactly. So again, we can't get exactly 20% duty cycle, but we can get pretty good darn close. And that's because we're going at a pretty fast rate here. That 32 kilohertz is pretty fast. We need questions, because this is always a confusing thing for folks. So I know you guys don't have it perfectly in your head. So do we have any questions about this? Let's do another example then. Okay. So as I said, we probably won't go any faster than 20 kilohertz, but we definitely will go slower. And there's some signals that we, especially for driving these little motors called RC servos, we go at a much slower rate. And we got to think about that too. So let's think there. Again, now we want let's do an example. We want 150 hertz. Actually, what we're going to use for the RC servos is 150 hertz. But let's just do this example for 150 hertz. Okay, now we've got a different situation, don't we? And let's say, 10% duty cycle for this example. Okay? So again, we still have, let's start out this way, our 50 megahertz. Let's start out with a divide of 1. And so that gives us, for now, 50. I'm going to leave that blank because we're going to have to change that. And then that, of course, is causing TB counter to count up at that 50 megahertz. So what do we want to set PRD to? Well, we got to do the math again. How much time does TB period need to count up to? 1 over 150 now. Agreed? 50 hertz carrier frequency. That's the repeat rate. So every 1 over 150 seconds, we're going to start again. All right. Well, we did it just like here. Look, we took the 32 kilohertz, 1 over, times that, right? So it's the same thing. It's 50 million divided by 150. Agree with that? Okay, let's do that on the calculator. 150. What am I doing? Clear here. 50 million. 1, 2, 3. 1, 2, 3. Divided by 150. We've got 300. Again, I can't get one. I'm picking ones we can't get exact. That's okay. We want to set TB period to 300. 333. Okay. Besides Marius, who can tell me what the problem here is? How many bits are there in TB period? Yes. 16. What's the biggest number a 16-bit integer can be set to? 2 to the 16 minus 1. Unsigned, right? Because this is an unsigned thing. It's just counting up. There's no negative numbers in TB counter or TB period. 65,535. That's a problem. We can't fit 333,333 in that register. So what do? Are we out of luck? We can't create 150 hertz carrier frequency? What can we do? Yeah. Sure can. Beautiful. So we have the capability of setting this to divide by 2, 4, 8, 16, I think is the max. Let's see, 2, 7, no, more than that. 32, 64, or divide by 128 is what they allowed us to do. Okay? Now technically, up here, we could have, even up here, right, at these fast frequencies, we could have divided by something up here. What would happen is it made TB period even smaller, wouldn't it have? Less ticks. And then you have less resolution to set your duty cycles. Does that kind of make sense? So you usually want to divide with the minimum divide, so you have plenty of resolution to represent your duty cycles. So yeah, you could always divide by 128, but then you're not going to get as many commands to drive the PWMs at. So let's think about that. If we divide by 2 here, then what happens? This is 50 megahertz here. We divide, this is 25 megahertz when we divide by 2. If we divide by 4, this is 12.5 megahertz. See what's going on? Okay. So, well, we can just go by this 333,000 here too. We're probably going to have to divide by something, either 4 or 8, aren't we, to get that below 65,000. Am I right there? Something like that, right? Let's try divide by 4. Let's see what happens, right? If we divide by 4, we'll get 12.5 million. So we would take 12,500 divided by 150. Anybody got that? You want me to do it? So 12, 5, 1, 2, 1, 2, 3, divided by 150. Is it small enough? Ah, it's still not small enough. Okay? So we're going to have to divide by 8, aren't we? And when we divide by 8, that's, really this divided by 2, isn't it? So we do one more, divide by 2. Oh my, what did I just do? Escape. I screwed up. Divide by 2. So what, 40,000 something. See how that worked? So it is true, there are some really slow PWM carrier frequencies that we cannot get. Like if we divide by 128 and still, so like maybe a 0.1 hertz carrier frequency or something like that, you can't represent with these PWMs. But I don't know anything that's driven that slow, so I think it's okay. What do we think there? Let's do one more example. Let's do a, let's do a 400 hertz carrier frequency. Oh, I didn't do the 10% duty cycle, did I? You multiply whatever that period value is by 0.1, don't you, to get the 10% duty cycle. Okay, so 400 hertz, and what carrier? Let's do 75% duty cycle. Okay, so we'll start out with a divide by 1 again. Probably not going to work. So we have 50 million divided by 400. Do you have that, Marius? Or no? Oh, no, you just have the, I thought you had a calculator there. That's fine. No problem. All right, 50 million divided by 400. And by the way, when you check off this week for that exercise 2, I'm going to give you a little example like this. And you'll have to figure it out. I'll say, how do we create a X number duty cycle? Okay, so sorry. What did I just had the calculator right here. So 12, that's too big, isn't it? So 125,000 is what it wants to set TB period to. But we know that's bigger than 65,535. But that divided by 2 will work, won't it? 62,500. Am I right there? I think so. So we could set it to that, but then we've got to set the divide. Clock divide must equal, well, set to 1, which means divide by 2. Remember, clock divide set to 0 is a divide by 1. Clock divide set to 1 is a divide by 2. 2 is divide by 4, etc. Yeah. And that's all found in the data sheet, right? In the how-to, or the register guide for this PWM. So really important. Get that in your head that all the registers that we use in the PWM are 16-bit registers. So the biggest value that can be in there is 2 to the 16th minus 1, 65,535. Okay?